literature, doing more careful calculations, came up with numbers of something like 6,000 years as a time scale for ocean chemical equilibration of added CO2. But the basic upshot is that if we were inputting, let me try to do this, that in the oceans, really chemistry is controlled by two constraints. That there's stuff coming down the rivers that need to wind up in the sediments. And on long time scales in steady state, the riverine fluxes have to balance the fluxes to the sediments. I'm leaving aside mid-ocean ridges and clay interactions and so on. But so more or less, so more or less what's happening is we have a bunch of calcium, magnesium, so on coming down the rivers. If the riverine flux exceeds the deposition to the sediments, then the saturation level of the ocean starts building up. The CCD, the depth to which the ocean is saturated, becomes deeper. The saturation level of the surface ocean becomes greater. Both of those things lead to more carbonates winding up in the sediments. And eventually, they balance the alkalinity flux coming down the rivers. And so basically, on sort of time scales of multiple tens of thousands of years, the saturation state of the ocean is determined by the mass balance constraints between the riverine flux to the ocean and the sedimentary flux from the ocean. Meanwhile, the CO2 concentration of the atmosphere on long time scales is controlled by the need for chemical weathering rates to balance the volcanic flux, the flux of CO2 from volcanoes and mid-ocean ridges and so on. And so basically it's the relationship between silica weathering and geologic fluxes of CO2 that's setting atmospheric CO2 on long time scales. The mass balance constraints of ocean alkalinity are setting the ocean saturation level, and then the DIC, dissolved organic carbon, alkalinity levels of the ocean adjust such that these twin constraints of surface PCO2 and saturation state are met. And the thing is that on time scales, and so going back to this Cretaceous picture, why didn't the high CO2 concentrations matter for Cretaceous corals is because it wasn't, in the Cretaceous, the high CO2 levels were not producing low saturation states. In fact, the saturation states, if anything, were probably higher than today because the weathering rates were higher. You had a bigger flux of riverine material that needed to wind up in the sediments. And but CO2 does control saturation states on time scales that are short relative to ocean interaction with the sediments, which means on this decadal century or even to thousands of years, that ocean chemistry is very sensitive to CO2 inputs. And this is why the normal geologic past is not a good analog for ocean acidification, because in the normal geologic past, everything happens slowly. And so this is coming back to some of my dissertation work many years ago, that there was a comet or asteroid that smacked into the Yucatan Peninsula, which is a carbonate shelf and also had a lot of gypsum in it. And it's thought that if you do, so it's thought that due to shock metamorphism, a fair amount of sulfur came out of the gypsum and blew around the world and landed in acid rain. If you do the calculations, it's not enough it's only enough to acidify to cause undersaturation in the surface ocean. And once it gets mixed into the whole ocean volume, it just wasn't enough acidity to make a difference. The CO2, again, the CO2 that came off of there was probably small enough to be insignificant. There were also, because there was a sort of a global dust cloud that wiped out the sun and caused plants to die, there was also worldwide forest fires that might have brought the CO2 level up to something like 2,000 ppm, but again, just briefly, because it was just a one-time input of CO2. So there's plenty more on this since then. This is from Jim Zakos's early work, which is the first cores that really went through this boundary. So this is the boundary. This is around a 500,000 year period. This is the surface, Delcy 13 of surface planktonic foraminiferum. This is the benthics, and so that difference between that carbon isotope difference represents the fall of organic matter from the surface ocean to the deep ocean, and those two curves basically collapse together for 500,000 years or so, and carbonate accumulation rates went way down. One of the things that's still not really understood, by the way, is these carbonate accumulation rates never at this site went up, nor did this carbonate isotope rating go up. And it seems like there are a number of things after this boundary that never really came back, nor have they been really explained since then. But anyway, and at the same time, other organisms seem to do quite fine, like diatoms, which make their shells out of silica, did quite well. There's lots of people finding dinoflagellate cysts, so it looks like diatoms and dinoflagellates did relatively well, whereas calcareous organisms preferentially disappeared. That coral reefs are not found after the boundary, but I mean, this question of whether it was millions of years or hundreds of thousands of years before corals started being found, again, there's some controversy, but let's just say it's an order of 1 million years before coral reefs are showing up again in the geologic record. So there's a couple of points here. One is that the coral reefs, when they show up, about half the species when they show up again, it's mostly species that existed before the extinction event, and about half the species that were around before the extinction event survived the extinction event. And so, I mean, my mental model for this extinction event was an acidification that maybe lasted a year or two or something like that until that surface waters could mix down. And that it apparently killed off coral reefs, and maybe it lasted longer, who knows? And there's other things going on, like no sun at the same time. But that while you lost coral reefs, it looked like many corals colonies were able to survive as minor components of other ecosystems, but they weren't able to build that architecture of the coral reef. And I think this might be what we're seeing also in this century, is not necessarily the loss of all coral species, but the loss of coral reefs. And so the question might be, well, even if the coral survives, it might be that the fish species that uses the coral reef to breed in might be more threatened than the coral itself. The other thing I wanted to point out is that how did the carbon cycle function this time when you lost all these calcifiers? And basically what happened is you got a micritic calcium carbonate deposition, so you have some kind of photosynthetic organism. Right next to the photosynthetic organism, they're extracting CO2 from the seawater, and so there's some microenvironment that has relatively high saturation with respect to carbonate minerals, and so then you get sort of biologically mediated abiotic precipitation of carbonate. That seems to have been widespread at that time. So, so just the other piece here is there's been other studies on this, but the basic conclusion is that when you lose biodiversity after mass extinction events, the characteristic time scale to generate that same level of biodiversity is on the order of 10 million years or so. And so, I think, I think the ocean acidification question is relevant here, that, we're going to be affecting biodiversity in a way that's going to affect, right, so the chemical changes will take, say, tens of thousands of years to recover from. But it looks like the biological and if you assume that that there's nothing that you could throw in the ocean that would keep it poisoned for more than tens of thousands of years, nobody knows of it. But that it's thought that why did it take 500,000 years for the KT boundary to recover? That there was just the time scales of evolving new organisms and ecosystem, which I don't know if I buy it. It just seems so long, especially for rapidly reproducing organisms. But also the time scale for the reefs to populate the coasts seems to be at least in the hundreds of thousands of years, and some people think in millions, but at least hundreds of thousands of years. And to recover biodiversity is in millions of years. And so the decisions we're making over the next years and decades are going to have impacts on this planet for tens of thousands to millions of years. So I know I'm running out of time here, but just to say that Wolfgang Kiesling and also I want to say Andy Knoll has done some good work. I'm going to just jump on this one from the Permo-Triassic boundary, where again the carbonate secretors preferentially became extinct. But I think this is a good indication of what we might expect in terms of patterns of damage for this century. And that is that, as I started off by saying, that things like corals, in this case brachiopods, but basically where the calcium carbonate skeleton is large relative to the size of the organic matter, organic tissue, and that the fluids are minimally buffered by the physiology. In other words, it's mostly just sitting in seawater. Those kind of organisms are what really get hit, and that then mollusks and arthropods less so, and then fish are even less so. And so I think in terms of organism, this general trend seems to be emerging that the more you're heavily calcified you are, the more your body fluids are close to unaltered seawater, like a sea urchin, the more sensitive you're going to be, and the more you're controlling your internal chemical environment, the less sensitive you'll be. Yeah, so just this is the big last thing. So I have a postdoc now who's basically gone back to what I started with that 2008 study with Long Cow that we did using our model. And she took the three scenarios, this RCP 2.6, 4.5, 8.5 from the CNIT5. And the reason she left out this 6.0 one is only 3 or 4 groups did it. I think it would be in the supporting online material. And just did the same calculation. And so this one is, you might call it business as usual. Some people think it's extreme for business as usual, but I don't. And I think I would call this one sort of extremely optimistic, and this one just I guess what's the word? Extremely optimistic and very extremely optimistic. So, but the depressing thing under this one is that even these don't look so good for corals. Okay, so this is the temperature records from these ones, and so if we look relative to anyway, it depends on where you count as the baseline, 1990 or pre-industrial. But this, if you're counting from the pre-industrial, 2.6 is like 2 degrees warming, and the 4.5 is 3 degree warming. And if you're counting from 1990, you could take off more or less a degree out of each of those. But okay, so this is. So again, this is the same kind of thing. This is now going through, happens to be for 8.5. This is the coral locations, and this is the aragonite saturation. And more or less, so there's 3 lines here, which I drew in the wrong color. But, so here's pre-industrially. In this case, there were mostly, I think there was not any in this analysis, less than 3.5 pre-industrially. And, here we are somewhere around today. And, very quickly, the chemistry of the water surrounding reefs ends up being non-overlapping with the kind of water that surrounded them pre-industrially. And so if you look at, so this is for 3 scenarios. So one of the questions is what is the aragonite saturation threshold that you should be using? And now we're up to 339, but if you look at when this begins, here we're about to cycle through again. Here, that basically it's all rated 3.75, and so you might think, well, 3.5 is a reasonable threshold. There's one other point here: sustainability versus killing off a reef. That it's much easier to continue occupying a territory that you already have, and so just because the water becomes less below some threshold doesn't mean the reef disappears right away. Anyway, there's uncertainty about what the threshold is, but if it's really 3.5, even in RCP 2.6, which starts bringing down emissions right away, something like half the reefs are unsustainable. And if it's aragonite equals 3.0 is this limit, then under 2.6, 90% of them would survive, would not be threatened by ocean acidification. But if you go to RCP 4.5, which is considered pretty great, if you can actually do that from a energy system point of view, that if the sort of survival threshold is really 3.5, even under 4.5, almost all the reefs are gone, and you get to if there's the more conservative, remember there's basically nothing. On our earlier analysis, only 2% of the reefs were surviving, less than this. And in this reanalysis of the CMIP 5, there's no reef today that's below, by open ocean waters, less than 3.5 as determined from these CMIP 5 models. And there's some caveats in there, but in the base case of this set of simulations, every reef was greater than 3. And then the RCP 8.5, it doesn't matter what the threshold is. We're zooming past it, and maybe it'll take us 10 years sooner or later to zoom past it, depending on what the threshold is. But so the basic upshot is RCP 8.5, it doesn't matter what the threshold is, they're gone. For these lower ones, which would be really amazing if we could have energy policies that would achieve one of these, it's still looking a bit dicey. And I have to say, I reviewed a paper that was looking at the temperature results of this, and the temperature results are maybe even more depressing than the aragonite, the ocean acidification results. But I think they're more, anyway, we'll go with that. So I know we're going to end here. So this is, again, this is putting those 3 different RCP scenarios on top of each other and just plotting them by, these are the 3 ones for the 3 thresholds, but this is all 3 RCP scenarios plotted on top of each other. And basically, what it says is in these CMIP 5 models, in the tropics, away from upwelling zones, which is where coral reefs are, the PCO2 of the surface water largely tracks the atmosphere. And whether you get to 500 ppm or 400 ppm on one trajectory versus another makes almost no difference for surface ocean chemistry. That the only thing that matters is the PCO2 level and not the trajectory by which we get there, if it's happening on a sort of century time scale. Okay, so I'll stop there. Sorry for going on too long.
Any other questions from anybody?
So what would you offer as solutions?
I mean, I think we need to transform our energy system to one that doesn't use the atmosphere as a waste dump, basically. That's all we need to do. No, but it seems to me we need to do it fast. I mean, we did a study on what happens if we just stop building any new devices, power plants, automobiles, but still let the existing ones that have their normal lifespan. And you get something that's not that far away from RCP 2.6. maybe goes down a little faster than that, but more or less, I think if we're serious, that we're almost at the point where we just have to stop building more stuff that dumps CO2 into the atmosphere.
Do you see a way if you lose 90% of the reefs of bringing them back more quickly than has happened before?
Well, I mean, I think it's interesting that species that show up in the Caribbean don't show up in Indonesia. And, there's a piece of me that would think that after millions of years, there's no polyps that got from one place to the other and managed to invade that space successfully. And so, it is surprising how, to me, it's surprising how geographic, how they don't seem to be able to spread well. And I would think that they're, the same way that people are talking about moving oak trees and planting them at the northern end of their range. I guess the thing with thermal stress, thermal stress and ocean acidification are really different, right? Because the planet's been hot in the past, and corals did fine. And you might say, well, they had more than a few decades to adapt to that. But, the tropics were always saturated with respect to carbonic minerals, except for these mass extinction events. And, they've never had to calcify in low saturation waters. And so, I think if the only issue were heat stress, the idea of moving warmer water species to places where it was cooler. There are a few places, like I think somewhere around Hawaii, there's a few places where corals are growing with saturation less than 3.0. I think Hawaii is one. And, so maybe studying those systems and, one of the things is this, everybody is so worried about, about biological, you can never get a permit to take a coral colony from Hawaii and bring it to the southern end of the Great Barrier Reef and stick it there to see if it will grow. Just because they'd be afraid of invasive species and all this kind of stuff. But, it does seem... anyway, obviously, I think studying the few places where corals have been found growing in low saturation places and trying to understand why they're surviving there. There was one in the Rob Dunbar was studying one coral colony somewhere in the Galapagos, and which was one of the lower saturation areas because it was upwelling water and it was all this carbon-rich deep waters, and I think starfish and things, and sea urchins, I forget what else, but more or less it was 1 year it was just gone and didn't come back. So I would say transplantation for temperature seems like it might work, and it's probably worth investigating for corals. But I think in terms of the field work, it's going to be hard to get permits to do things. But it does seem like it would be useful to know. Yeah, I would think if you were in Australia and you had a choice, it's sort of like in France, they had some disease of their grapevines, and they ended up bringing in plants from California back to France. And I would think that even right now, Australia, with their cane toads and all that, is very worried about invasive species and wouldn't let you do anything. But I think if they had a choice of having no barrier reef or a transplanted one, they would go with the transplanted. No, that's probably that's probably a good research direction.
Any other questions?
Talk them down. Yep.
So I recently read back when Christine Gregoire was governor that she spent like $3.3 million on putting like a war on ocean acidification. And
Who is this?
the governor. And she said that one of the solutions they're thinking of implementing is planting eelgrass, and this was just for Puget Sound that they're working on. Have you heard of this?
No. Yeah, so this, but there's similar stuff came up around Stanford, this discussion of, California's response of if the primary cause of the problem is global CO2 emissions, what does the California ocean acidification research program look like? And, and I think there's a few dimensions to that. One obvious one is one that's obviously that impacts, whether the California's or industries along the coast that might be impacted. And then the other there's another component that has to do with every organism, you can think of CO2 and ocean acidification as another stressor on organisms and ecosystems. And so, okay, let's reduce other stressors to the maximum amount possible so that organisms and ecosystems are more resilient to ocean acidification. And then the last question is, can we do something locally to actually do something about ocean acidification directly? And I think we need to divide sort of bays and estuaries from open ocean environments. And my sense is that for open ocean environment, that the amount of sort of change to the pH caused by the local point sources or even distributed local sources is tiny compared to the mass of water involved, and that nothing you're going to do locally is going to substantially change pH, at least at a regional scale. Somebody wants to argue with me, it's fine. Now, the other thing now with estuaries, I don't know that much about estuaries, but I think a lot of the chemistry of estuaries is governed by the water flowing into the estuary from the freshwater side of it, and that a lot of the dissolved inorganic carbon in these systems is from organic matter that have more to do with nutrients and local cycling and algae and so on, and less having to do with the atmospheric CO2 concentration. And then, and so in my mind, the ocean acidification is more directly an open ocean problem. And now, obviously there's things that spend their life cycles going between these different environments. But in other words, I'm not clear of how much, if you have an estuary that, say, has too much phosphorus and stuff, too much nutrients going into it that's making algal blooms, that's then rotting, making anoxia, and then high DIC concentrations. How much is that DIC concentration elevated because the atmospheric CO2 is 450 ppm instead of 350 ppm? I'm sure there's people here more expert on this than me, but I would think that the change in atmospheric CO2 concentration is not the primary insult on that estuarine ecosystem. But so yes, if those nutrients, I guess then there's all kinds of complex questions. So let's say those nutrients are making high DIC concentrations. Is there some reason to call that ocean acidification and saying we're helping ocean acidification by this, or you're helping some? Anyway, it's a tough question, but my own view is that the regional things are really having to do with regional impacts and other stressors to those ecosystems, but the ocean acidification, the causal agent is primarily global CO2 emissions, and then I'm a little bothered by people who say we're going to deal with California's ocean acidification problem by dealing with California's pollution, and somehow that's going to solve the problem for California. I don't buy it.
But it's additive, isn't it? I mean, so if you have eutrophication, you're going to add phytoplankton blooms in your estuaries and maybe cause estuarine acidification on regional scale, so, I mean, there's merit to it both.
Yeah, no, I mean, it might, I mean, yeah, I mean, I have to also see a study of it that, I mean, I guess this come up in the sort of, right, why do you worry about acid rain in lakes? And we're not really worried about lake acidification from CO2 that much. And it's not, and it is true that in, say, if you had a granitic lake with a few cations, its pH would change. Anyway, let me maybe back off of what I said a little bit and just say that it would be useful to do research to show, say, in an estuarine system, how much does the atmospheric boundary condition
On the west coast, so we have acidified upwell water that comes in the estuaries during the summer months. So, on the Washington Oregon shelf, so I mean, you have local processes, and you have the open ocean influence as well.
Yeah, but of course, yeah, so the question is, I mean, let's say if the excess DIC due to anthropogenic CO2 is 60 micromoles per kilogram. So the question is how much does this other 60 micromoles per kilogram make a difference in that system? I don't know the system. I shouldn't be talking about systems I don't know about. I'm trying to say the basic answer, but I would say that if it hasn't been published, somebody published a paper for an estuarine system where they run the model under 390, 300, 400, 450, and shown it would be a useful study. Yeah, I don't want to overplay. I'm talking about things I don't know about.
Any further questions? Let's thank Dr. Caldeira one more.